Today's third and final video, I'll talk about what you would do if you wanted to model the vapor and liquid phases both as ideal solutions. I want to mention that this requires a couple things. The first is that it requires that the pressure is high P, and that is because if you wanted to model the vapor as an ideal solution, remember the difference between an ideal solution and an ideal gas, that an ideal gas assumes that there are no interactions between the molecules, while an ideal solution assumes that the interactions between molecules of different types are the same as molecules of the same types. So because the vapor molecules must interact with each other in order for them to be modeled as an ideal solution. And the second thing I wanted to mention is that this is not a very common method. It's possible, but not common. Possible, but uncommon to perform this type of analysis. That's because typically at higher pressures, you have some non-idealities as well. Okay, I'm just going to go ahead and write the equation. Remember that we start with equating the mixture fugacities of the vapor and the liquid phases. So F hat I of the liquid phase is equal to F I hat of the vapor phase. And because this is an ideal liquid at high temperature, gamma is equal to 1. Gamma I equals 1 because we have ideal case. But the fugacity, the pure component fugacity, needs the Poynting correction. And FIL needs Poynting correction because we are at an elevated pressure. So I'll just put that in parentheses, high P. So the liquid side looks kind of like before, XI, PI set, exponent of molar volume of component I, P minus P set divided by RT. This side of the equation looks similar. The only difference is that there is no gamma because, as I said, gamma is equal to 1. On the vapor side, it can be shown, but I'm going to skip the showing of this, that the fugacity of the vapor is Yi times P times the pure component fugacity, not the mixture fugacity, over phi I set. And this phi I set came from the left-hand side. I just divided it over such that we have vapor and liquid sides. So the two differences from above, two key differences, are that gamma I is equal to 1, so it drops out of the equation, and I have phi I hat turns into phi I for the ideal solution. So I don't have to go through the trouble, or I could go through the trouble of calculating what the mixture fugacity is, but it'll simplify a little bit if I only take into account the pure component fugacity. So for example, in the virial equation of state, so for the virial EOS, what was the expression for the mixture fugacity of component I? Looking at my notes, I'm just going to do the mixture fugacity of component 1 because that's what I have, and then the same thing will hold true for component 2 as well. It's P over RT times B prime 1 1 plus Y2 square 2 B prime 1 2 minus B prime 1 1 minus B prime 2 2. And if I have if I'm looking for the pure component fugacity, that's what phi I is. So for phi I, or for phi 1, which is pure component 1 fugacity coefficient, this is signifying, because it's pure, that y1 is equal to 1 and y2 is equal to 0. So if y2 is equal to 0, all this stuff drops out. So this 0 kills this whole term. And I'm left with the pure component fugacity for component 1 is equal to simply P B1 over RT. And same thing for phi 2. P B prime 2 over RT, where B1 and B2 are calculated just like normal virial second coefficients. So how would you go about solving a problem with this information? Let's say the goal is to, just a quick example, I'm not going to go through the whole thing, I'll save it for Friday. A quick example of making a PXY diagram at a given temperature. So T is going to be given, and then X or Y will be set, and the unknown variable will be P and whichever one of X or Y we did not set. So to calculate the bubble point, once again, just like in Routh's law, we are using the constraint that y1 plus y2 equals 1. And we are solving for y1 or seeing if it'll drop out. So in this equation, if I solve for y1 and add these all together, I can come up with the following. I could say that P is x1 P1 set over phi1 divided by phi1 set. And remember that phi1 set is just the fugacity evaluated at the vapor pressure times exp molar volume of component 1, P minus P set over RT, and then plus 1 minus x1, which is x2, times P2 set over phi2 over phi2 set, exponent of molar volume 1 times P minus P set all over RT. Okay, so if we set x1, remember we're setting a range of x1s from 0 to 1. We can, if we're given what the temperature is, we can evaluate what the vapor pressure for component 1 and component 2 are. We would have to look up the molar volume, so that's something you'd need to look up. And phi would be given based on this equation. So phi1 has a P in it, right? So phi has a P in it, and phi set is evaluated at P set. So phi1 is equal to PB1 prime over RT. So you also have to look up B prime 1. Well, let me continue writing these things out. Phi1 set is P set 1. So that's what I mean by evaluated at the vapor pressure. P1 set, B prime 1 over RT. T, remember, is set. I might have to look up B prime 1. I'm sorry, I'd have to look up V under bar 1, and I would have to calculate based on virial coefficients B prime 1, 1, or B prime 1, and P set 1. All right, I think that would be all I would have to calculate and look up. And obviously the same thing for component 2 over on this side. But this would be one equation for one unknown, provided that x1 is known. There are no other unknown variables here. Just P is the only unknown, and P is involved there, there, and there. All right, so definitely use solver or goal seek. Also, P is involved there and there as well. Because there's two terms, right? So I have to look up V1 and V2. These are both pure component molar volumes. All right, after I know what the bubble point pressure is, I can calculate Y1 by plugging it back into either one of those equations. And I can obtain X1 P1 set over phi1 over phi1 set exponent of V under bar 1 P minus P1 set over RT. All over this whole term again, X1 P1 set over phi1 over phi1 set exponent V1 P minus P1 set over RT plus the same one for component 2. 1 minus X1 P2 set phi2 over phi2 set exponent molar volume 2 P minus P sat 2 over RT. All right, so this is how you would solve for the unknown variables, P and Y, given your range of X's. And then when you're finished with that, you can simply plot P versus X and P versus Y, and you have a PXY diagram. Friday, as I said, I'm going to be doing a lot of example problems, probably do 2, maybe 3 if I can fit them in. I think these problems are going to be a little bit longer. I'm going to show you how you would calculate everything using Microsoft Excel. See you then.